3 months ago, we packed our bags and got on a plane to Barbados. There were a total of 17 of us embarking on McGill's Barbados Interdisciplinary Tropical Studies at Bellairs Research Institute. Throughout the program, we would learn about agriculture, energy, and socioeconomic issues that were specific to Barbados. As part of the program, each student chooses a project to work on throughout the entire summer. Dom, Carmen, and I all chose the greenhouse project. And this is what we did over the past 3 months. The greenhouse project would consist of 2 interrelated parts. The first part was building the foundation, frame, roof, and floor of an NVAC greenhouse on the Bellairs grounds. The second part was replacing the misting line in a previously constructed commercial-sized NVAC greenhouse, and then trying to optimize that misting system. The majority of our efforts over the summer were focused on constructing the greenhouse at Bellairs. What we learned from installing and operationalizing the misting system in the commercial-sized greenhouse would inform how the misting system would be installed and operationalized in the final stages of construction of the Bellairs greenhouse.
Barbados is a SIDS country, a small island developing state. It means they can't take advantage of economies of scale just because they're not large enough, production isn't large enough. Also, there's seasonality problems. There's not distinct seasons, which means that a lot of pests and diseases, which would typically disappear on the changing of the season, they're around all the time here, which means that growth can be really hard. The other thing is a loss of arable land. So most of the ground here is a coral limestone, which makes it harder to grow. And what arable land there is being converted into a lot of tourism industry. So they're losing agricultural land that could be used for productive reasons, and it just means that they end up having to import, so their food bills are quite high. And so that's where the greenhouse comes in, is trying to increase local production and consumption.
A greenhouse is a form of protected agriculture that produces a controlled environment for plants to grow and thrive in. It protects plants against rain, pests, diseases, and many other threats, but one of its main features is turning light into heat. This conversion takes place when sunlight enters through the roof and walls of a greenhouse. Part of this light is absorbed by the soil and plants. Part of this light is reflected off of the greenhouse walls and roof as infrared radiation, trapping the energy inside the greenhouse, and part of this infrared radiation escapes the greenhouse. The net effect is that the temperature inside the greenhouse rises. In temperate regions, greenhouses are used to prolong the growing season. However, in the tropics, where there is more solar radiation than in temperate zones, the greenhouse effect can cause the temperature to rise too high, to a point where the high temperature is detrimental to the plants. Ph.D. candidate and our mentor, Lucas McCartney, along with his supervisor, Dr. Lefsrud, are currently developing technology called a naturally ventilated augmented cooling greenhouse, or NVAC greenhouse, to remedy this issue of temperatures rising too high in tropical.
The goal of the NVAC system is to provide ventilation and air movement in a tropical greenhouse.
The conventional greenhouse that we're basing the NVAC design off starts off with just a row of 3 columns of parallel steel bars, with the middle one taller. This is the apex of the structure. Then, as I said, the conventional one, it traditionally consists of the first roof, which is the tallest right here, but also the second roof right here. And this space is open so air currents can leave and go, as are the sides of the greenhouse. What the NVAC design brings to the table is a third roof right here. This is suspended by just metal bars from the top. Also, there is a misting line that runs the entire span of the canopy, located at the tip of the third roof right here. The NVAC greenhouse, or also known as the naturally ventilated augmented cooling greenhouse, works under the simple principle of convective heating and cooling. This is done by injecting small droplets of water into the air from the misting line, which then cool down the air in the headspace between the third and the first roof right here, causing the air to chill and sink, like in this with this pink line. This cool air then fills the voids in here and pushes out the hot air, which is naturally lighter than the cool air, which also rises. This fills the headspace underneath the second roof, then exits through the gap aforementioned earlier, causing a cyclic air current in the greenhouse itself. This cyclic air current cools the plants in two ways. Firstly, the current replenishes the air inside the greenhouse faster than it usually would without the misting system inside. This takes out the humid hot air at a faster rate than the sides do anyways, therefore cooling the plants. The other way that the cyclic air current cools the plants inside the greenhouse is by implying a convective heat transfer on the plants themselves.
The greenhouse here at Bellairs is being built as, I guess, another NVAC greenhouse that we can use as a proof of concept.
It's an amazing learning tool, and not just for students and people who study at Bellairs, but people on the island. Part of the BITS program or the BFSS program, they're going to be able to use the greenhouse and learn how they work and to build on them and to grow things and to take that back to Canada.
Here at Bellairs, meals are served for the students that are attending in the BFSS program or in the BITS program. They get lunches and dinners throughout the week. So the idea behind the NVAC greenhouse here at Bellairs is to provide a growing area for fruits and vegetables that are used in these meals right on site. So it would be very local and more sustainable food, seen as a lot of these fruits and vegetables are still imported into the country.
It's a really great tool to be able to take what you've learned in the classroom and actually do it and to see it happen in real life and to learn that way. So regardless of how much it's producing or how much it's reducing food bills at Bellairs, regardless of whether or not it succeeds in that way, it's still an extremely important tool.
We rented a bobcat to drill 12 holes, which would form the basic foundation of the greenhouse. Each hole was roughly 1 meter deep.
The location for each of the holes had been previously mapped out, using stakes in the ground and string in order to make sure they were equal distance. We inserted sonotubes into the holes. Because of the sandy layer, this would prevent the holes from collapsing onto themselves. We calculated that we needed 3 cubic meters of cement for the foundation. We manually poured the cement into each of the 12 holes. We manually packed the cement using wooden sticks around the angle irons. The angle irons that we cemented into the ground would later be used for the vertical members to be attached to create the frame of the greenhouse. We had to make sure that each angle iron was equal distance from each other and to make sure that they were level. In order to do this, we used string and levels and the help of Bellairs students. The extra concrete was used to make a box, which we then wrote our own names on, including SPF McGill and our mentor Lucas McCartney and his supervisor Mark Lefsrud.
We calculated the grades, lengths, and quantities of the steel we needed, then went to Williams Metals, where we purchased the metals and got that delivered back to the Bellairs yard. Once back at the Bellairs yard, we started construction of the frame. The metal was cut to the desired length using the hacksaw. On the next project day, we also started helping in the construction of the frame. This included making the lower roof member, but also the middle members. This was done by using grip clamps to position the metal and then just drilling holes in the metal and putting the bolts through. And through the duration of the project, there was significant amounts of drilling. And drilling, and drilling, and more drilling. As you can see by my face in this clip, we did some more drilling, and more drilling. Oh, look at that drilling, and drilling.
With the frame completed, it was time to start on the roof. Again, we did some calculations. This time it was to find out how long the metal tubes we were going to buy needed to be when they were straight, so that way they would be long enough once we bent them. The bent metal tubing would form the 3 roofs of the greenhouse. We then trimmed the tubes with a hacksaw to the lengths that we had calculated. This is our bending jig. We used it to bend every single roof member to the same angle. To test if the roof members were identical, we'd laid them on top of the original tubing we bent. Once we were satisfied that all 3 groups of the roof members were identical, it was time to start installing them. We fed both ends of the roof members through the U-bolts that we had previously drilled and bolted into the frame. To make sure that the roof members stayed in place, we tightened each U-bolt. We also had to figure out how to reach the tallest roof members, since we didn't have a ladder that was long enough. To do this, we created a movable platform with a piece of plywood and 3 metal bars, which we could then put a ladder on top of. We climbed up the ladder on this platform to do the same process of threading the roof members through the U-bolts and tightening the U-bolts. The final phase of the build was to have the floor of the greenhouse installed. We ordered a huge pile of crushed coral, which would become the floor. A man named Selwyn was hired to dig 1 foot deep in the interior and 1 foot outside of the perimeter of the greenhouse. Selwyn then filled the hole with the crushed coral and piled it 6 inches above ground level. The last step was to compact the crushed coral, and the floor of the greenhouse was completed.
Preview.
So last summer we successfully overhauled a commercial greenhouse and turned it into an NVAC system by putting a new roof inside the greenhouse and putting in a misting system, including all the pumps and filters and whatnot. This year with the students we overhauled the misting system itself, so improved it and turned it into a better misting system.
The problem at hand was to replace the beige misting line put up by last year's group, which had become blocked by algae. Reaching the canopy height with ladders was possible, but taking down the meshing was very time-consuming. We solved this by devising a system that leapfrogged a large metal beam and a 2-piece ladder across the roof's cross beams. And yes, it was as sketchy as it sounds. Once at the canopy level, we removed the tube clamps and cut down the misting line. Although on paper it seemed like a simple task, maneuvering at elevation along the span of the greenhouse took enormous amounts of time.
Putting up the new misting line required climbing up ladders again, 15 feet off the ground. A black misting tube was used to limit the amount of light filtering into the tube, which would prevent algae from growing inside the tube. The misting line consisted of 24 nozzles. 12 nozzles had filters and 12 did not. This was to test if filter use was advantageous in avoiding buildups in the tube. This is the basic floor plan of a commercial greenhouse. There were a total of 5 sections of the misting line dependent on where support beams were on the roof. We placed a ladder across 2 horizontal irons supporting the roof to attach the misting line to where there was no pole for us to move along. After each section was done, we had to move the ladders and angle iron to the next section. The misting tube had to be fastened to a steel cable running along the roof of the greenhouse. To attach the misting line, we used clamps to fasten the tube to the steel cable. We used a screwdriver to tighten each clamp.
The owners of the commercial greenhouse had reported back to us that they have noticed changes happening in the greenhouse when the misting system is operationalized. One area that they saw a significant change in was a reduction in blossom end rot. The owners of the commercial greenhouse also told us that the misting system, when it's in operation, does seem to lower the temperature of the greenhouse. This means that farmers can lower their input costs.
Last year's misting operation was actually cut short after the bits group left Barbados. Last year's problem was that algae This year's problem is different, however. Limestone seems to be the culprit, and while it is inconclusive, at some point in time we believe that the system or the storage tanks itself became contaminated with calcium carbonate or limestone. And this has caused our filter nozzles to block up within a week actually of operation. So because the normal nozzles themselves are still running no problem, a recommendation would be to replace all the filter nozzles with the normal nozzles, and I think
went up to the third roof of the greenhouse to remove the filters that had been blocked. As we said before, the misting line was comprised of 12 nozzles with filters and 12 nozzles without filters. When we had installed the misting line, we thought that the only difference between these two types was whether the nozzle had an accompanying filter or not. However, when we removed the filtered nozzles, we discovered that the filter nozzles were actually composed of 4 parts: the nozzle, the filter, a pin, and a spring around the pin. When we removed the filter, the pin and spring came along with it. This caused the nozzles to spray a jet of water into the air instead of a fine mist. So, we had to shut off the misting system. Because the nozzles were imported from Canada and can't be found on the island, we had to leave the job of replacing the filter nozzles with regular nozzles to the fall group of students who will be working with Lucas.
Some recommendations for the project. One of the main things that went wrong in the project was that our data collection was cut short due to us running out of water. The water source we got was from just rainwater, and the roof that was used to collect it was not sufficient area to produce enough water for the 105 liters an hour required to run the system. My recommendation is that the rainwater collection tanks used for the misting system be connected either to the overall grand irrigation system of the greenhouse, and if that was not possible, maybe hook up another part of the rainwater collection system to a slightly larger area that would provide sufficient water for the system itself. It was far too little water.
Safety was a big issue in our project.
My safety was at risk sometimes. There's a couple times being high up, standing, 15 feet in the air on a angle iron, and I was a little nervous.
We just didn't have the proper materials, like proper ladders or scaffolding or any kind of safety device that would allow us to work at high elevations without enormous amounts of risk. If I could change something about the project, it would be to make sure that there is proper safety equipment used.
Maybe next time I would get more, ladders and scaffolding.
Definitely one of the lowlights was the amount of drilling that we had to do. It was just, at times, never ending. And what would have been fine if we had high quality drill bits became very not fine due to the materials we had at hand, and it was just very painstaking and laborious. And maybe that's me being a crybaby, but I thought it was tough.
Working with Brittany and Dom was great. As soon as we all met, it was just really relaxed, really chill. We all got along really well. We all kind of have different backgrounds, which meant that we all brought something different to the table, and I think that was really important in a project like this where it demands changes, it demands going with the flow, it demands different perspectives.
Working with Dom and Carmen on the project was really great. We all fell kind of seamlessly into our roles.
Working with Bray and Carmen, it was the worst thing I've ever done. I actually really enjoyed working with Bray and Carmen. They both brought their own aspects to the team and put up with my downsides at times, and I appreciate that because I know it can be hard to work with. But all in all, I was happy with my team members.
So how am I feeling post-project? I feel proud. I feel accomplished. A little bit tired. No, actually, in all seriousness, it's quite cool to see the knowledge that I learned in a classroom and through my 3 years of studying to actually formulate into something that I built with my own hands and that you can see, and that'll be at Bellairs for a really long time. And that feels pretty cool.
Post-project, I feel pretty proud about what we did. It was a lot of work, a lot of building, a lot of reports, and I'm very proud of our final product.
Post-project, I feel very accomplished in the amount of work that we did in the actual time we spent building. The first time Lucas was here, we built a greenhouse from nothing, effectively, so that's something I'm proud of, and being able to be part of a project that's of a medium scale was a cool thing just to do too. We had definitely huge input into the project in terms of decision making, of the design, the materials we chose, the way we went about it, the way we fixed problems that occurred. But it was cool to see that's how some of our ideas